Hello, everyone. My name is Jeffrey Paz Buenaflor. I'm a postdoctoral researcher in the Wissinger Group at the University of Minnesota. And today I would like to talk about two new teaching labs I developed over the past year that incorporate sustainable polymers into the chemistry curriculum using hydrogels, which are water-absorbing cross-linked polymers that have wide usage in biomedical and hygienic applications. Bringing sustainability into the classroom is a great way of improving our teaching to build interest, relevance, and self-efficacy with our students by connecting chemistry to real-world problems and showcasing current state-of-art innovations from research and industry. For the two teaching experiments, they incorporate sustainability in this matter, where for the edible water capsules, high school students explore a edible material that can be derived from algae as a potential alternative for petroleum-based plastic water bottles. For the disaccharide-based hydrogels, undergraduate students can synthesize a material using a monomer that can be derived from the dairy waste feedstock. For the synthesis of the water capsules, high school students reacts food-grade sodium alginate with calcium lactate in an ion exchange reaction to generate this cross-linked polymer. To do that, they can use either a spoon or a dropper to dispense the solution of sodium alginate into a calcium lactate bath to generate these type of capsules. In terms of an extension for the experiment, students can utilize varying concentrations of citric acid to modify the pH to see how it can affect capsule formation and shape as shown here. We can get spheroid shapes to more ellipsoid and then more oblate structures. Students are taught acid-base chemistry and the relationship between pKa and pH, and then they can take that knowledge to predict which beverage juices can form a capsule. For the methacrylate hydrogel experiment, undergraduate students can take lactose, which can be sourced from whey, the liquid waste that remains from the straining of milk, and react it with methacrylic anhydride, the cross-linker in this reaction, under basic conditions to generate this mixture, which can then be irradiated using UV light to generate the cross-linked hydrogel. Upon synthesizing their hydrogel, students can then explore their mechanical strength and swelling behaviors, as well as changing the cross-linking densities to tune these properties. For the compression test, students take this disc and break them in a compression instrument where they can obtain stress-strain curves and measure their relative elasticities. For the swelling behavior, students bathe their hydrogels in aqueous solutions for a set amount of time to generate these materials that absorb water. And in this case, they can determine how much it takes depending on the cross-linking density. And then they can take their dried form and compare it to a commercially available product, such as sodium polyacrylate, which is a material found in diapers. So I showcased two experiments. The next step is to bring them to their classroom. The edible water capsule will be tested in an AP high school, AP chemistry high school classroom in the near future. The sugar methacrylate hydrogel has been tested this past spring semester at the University of Minnesota and Augsburg University. The improved teaching experiment will be tested again at Augsburg University this fall semester. Thank you for listening.